Kids, hey, modern physics, general review part two. All right, so first part we talked about was how light behaves like a particle. I should have mentioned there's two equations I didn't say, so let me just refer back to those two equations from the first part just so you have it. First, we said that temperature. Remember, temperature relates to energy, and we said that energy relates to frequency, so that if you were trying to find which relates to 1 over the wavelength of our light, which gives us this equation, which is the most common wavelength. So it's not like the highest wavelength, it's just when they say max, it's the one that is given off most, is equal to a constant, which the constant is, I actually have to look this one up because I don't remember, 2.9, I think, times 10 to the minus 3. Oh, I didn't remember. Over the temperature in Kelvin. So B is a constant, which is 2.9 times 10 to the minus third. And then the units would be meters times Kelvin, so that you end up with meters, okay? But this will just tell you, hey, if you have a star and it's at a certain temperature, you can figure out what is the maximum wave, or the most common wavelength that's going to be given off, okay? That's what that equation is. And then the other equation that I didn't talk about was this equation. Power, not momentum, power, capital P, is equal to surface area times a constant times the temperature raised to the fourth power. Again, this has to be in Kelvin. This is the surface area, so that if you have a sphere, you have to actually use the equation for the surface area of a sphere, which it's on your constant sheet, so you have it. And then this would be in joules per second. Sometimes they'll do things like, hey, power per meters squared, and then it's just this times this, where this, okay, is a constant, which is 5.67 times 10 to the minus 8. And the units would be, just so that I get watts, would be watts over meters squared times Kelvin. But there you go. So just make sure you are familiar with those two equations. This one you'll sometimes see where they do proportional reasoning. Hey, if the temperature is times 2, what's going to happen to the power? Well, times 2 times 2 times 2, 4, 8, and then it would be 16 times bigger because it would be 2 times 2 times 2 times 2. Okay? But there you have it. So that was the other two equations I forgot to mention. So now I mentioned them. All right. Then, second part. This part is going to be all about photon emission and photon absorption. Okay? And it really kind of comes down to the Bohr model and stuff like that. So if you remember, we ended with the de Broglie wavelength and his amazing algebra around the turn of the century, so this was in 1904, J.J. Thomson came up with a theory that, hey, you know what, maybe they were trying to figure out what is how an atom is set up. And so he's like, well, I think an atom is a bunch of positive mush. Here's the positive mush. And then there's these negative electrons that are just in there. And so he suspected if that's the case, if you send positive charge at it, which, what did he send? He sent an alpha particle. What is an alpha particle? It's a helium nucleus, 2 protons, 2 neutrons, and then they should just go straight through, okay? But in reality, what happened, which makes sense, if I have a nucleus here, or an atom, let's just say it's an atom, so I have some positive charge, and then I have some neutrons. Hopefully we'll talk more about that later. But if I shoot an alpha particle at it, So I shoot an alpha particle at it. I shoot a different alpha particle at it here. Well, this alpha particle is just going to move straight. And in fact, most of the alpha particles, that's what they did. They just moved straight because and Thomson was like, cool, hey, it's working. My model is working. But then every so often you would get an alpha particle that would get deflected like crazy, okay, which makes sense. And then Rutherford came up and said, hey, you know what? My model is better than Thomson's model, and my model is going to be, hey, the positive charge is concentrated in the center, which we now call the nucleus, okay? And the negative charge is going to be around the outside, okay? Which some people call the solar system model. Why? Because it sort of resembles a solar system. Like, here's your star, and here's the planets going around. And this was better as far as like what happened. Why it explained why the alpha particles sometimes would get deflected a ton, and most of the time would just move straight. But here's the issue with this one. Okay, this one says, oh well, wait a second. These electrons, okay, are moving in a circle. Okay, we know things moving in a circle are accelerating because what are the three ways to accelerate? You speed up, you slow down, you change direction. So these electrons are accelerating. Well, if you have accelerating electrons, they are going to give off electromagnetic radiation, which normal Joe Schmo calls light, which we know light has energy based on that equation. Well, if these electrons are giving off energy, they're going to lose energy because they're giving off photons. Well, if they lose energy, they're going to end up collapsing into the nucleus, and my atom is not stable. So Rutherford model didn't really make sense. Okay, and actually he also determined that as it falls in, it should give off all the different colors because you should have, it's giving off lots of different colors as it goes in based on this. Well, Niels Bohr came along and said, hey, you know what? Do you remember de Broglie wavelength, which was that equation, okay? And what he said is, hey, there are going to be certain wavelengths where this electron is stable, okay? It's sort of like a standing wave. So if there's one wavelength going around, that would be n equals 1, which is our different energy levels. So n equals 1 means you have one wavelength all the way around, okay? And that wavelength is based on, and he calculated based on this and this, the momentum. He knew the mass of an electron, and he figured out how fast that electron would have to be going to stay in a stable orbit. So he knew this. If he knows this and this, he can find the wavelength. And lo and behold, for hydrogen, it'll work perfect, okay? And then n equals 2, which is our second energy level, would be 2 de Broglie wavelengths. And n equals 3 would be 3 de Broglie wavelengths, and so on. And then he developed this model, okay, which is going to be the one that we're going to talk about next. Now, I'm just going to say this one is also not perfect, okay? But for this class, this is as far as we go. So if you want more than that, you got to take an additional class. So he developed this model. So he said, all right, you can think of the electron levels as sort of like a well. And we've done this before, like an energy well, where I'm going to call this n equals 1. And I'm going to call this up here n equals infinity. Infinity means that electron is not part of the atom anymore. It's off the atom. It's gone off into space. It's not part of it anymore. So this is here, and then you have these other energy levels in between. So this would be n equals 2 maybe, and then n equals 3, and then n equals 4, and so on. Now, first, a couple things that I just want to show you. You'll notice, hey, this gap is bigger than this gap, which is bigger than this gap, and so on. Well, that's for a reason. Remember this is not going to be our perfect model, but, okay, if you can imagine, I have these different energy levels like this, okay, where this would be n equals 1, okay? And n equals 1, there's 1 de Broglie wavelength around. This would be n equals 2 de Broglie wavelengths going around, and so on. Well, to go from here to here takes more energy than if I keep drawing, these would have to be circles all the way around, but if you imagine like going from here to here, it's going to take less energy. Why? Because here to here, it's closer to the positive charge. Here to here, you're farther from the positive charge. So hopefully that makes sense, which is why the energy levels need to get closer as they go further apart. That's important. And if I was to make up some numbers, let's just say this is negative 10 electron volts. This is negative 6 electron volts. This is negative, so if I want 4, then we'll go 3 electron volts, negative 2 electron volts. So if you look, the gap between here and here is 4, 3, 1, and then I would go off to infinity, okay? Or whatever, like I could keep going. But let's just make sense out of this. So Bohr's says a couple different things, okay? One, okay, this is sort of my energy level, so my electron could go from this level to here, this level to here, this level to there, and so on. That here's what Niels Bohr is saying, that electrons, when they jump from one level to the other, have to go from this to here. They can't go from here to like halfway. They can't go from here to halfway. They have to go from here to here, or they can go from here to here, or they can go from here to here, okay? Or they could go from here to infinity. This is called the ionization energy, because for an electron to go from this level, which was like here, to off the atom, it would take that much energy. So if the ionization energy would be 10 electron volts, so if my photon had 10 electron volts, where this would be 4.14 times 10 to the minus 15th, you could figure out the frequency and then figure out the wavelength of it based on that. If that photon had that much energy or more, it could make the electron jump, okay, and escape the atom, okay? But otherwise, these are the different things that would happen. And once you kind of make your thing here, then all you have to do is like, all right, if I have an electron in this level, which is where the electron wants to be because it wants to be closest to my nucleus, if a photon comes in, so a photon comes in and to my atom, and it causes my electron to jump. That electron could jump to there. If that photon had an energy of 4 eV, it could go from here to here. Now, if it only had 3 eV, it would not go from here to here. Do we understand that? Okay. But it could go from here to here because that's 3 eV. Okay. So if I had an electron in this level, it could jump to there. But it can't go in between. Okay. So, hey, it could go to this level. If I started at n equals 1 and I happen to absorb a photon with 7 eV, then it would jump to this level. If it absorbed a photon with 8 eV, it would jump to that level, okay? If it absorbed a photon with 10 eV, it would literally leave the atom, or if it had more than 10 eV, it would leave the atom and not be part of the atom, okay? So this would be absorption. Now, it could also, okay, this would be from 1 to something, but you could go from 2 to something. So it could be like, hey, I absorb 3 eV, and it goes from 2 to 3. Okay, I absorb 4 eV. It goes from n equals 2 to 4. It could be, it ionizes the atom, it absorbs 6 eV. It could go like that away from off the atom. And then I could do the same thing if I absorb 1 eV, it could go from there, or I could go off to the atom. Okay, that would be absorption. So absorption, my electron is gaining energy from my photon, and it jumps up to a higher energy level. Remember, you can't be at a gap. Okay. Emission is going to be the opposite, okay? Meaning the electron falls down to a lower energy level. Okay, remember, the electron wants to be closer to the nucleus, so it's going to make sense. If it has a lot of energy, it's going to try to fall down and get closer to the nucleus. Well, when it falls down, it has to fall from one energy level to the next. It can't just hang out in between, because remember, the stable orbits are when you're a full wavelength, a full de Broglie wavelength. So if we were to do that, okay, so hey, if I'm going to go from, let's say I have an electron that's hanging out in n equals 4, it could fall all the way down. If it fell all the way down, it would give off, so like you would have a photon shooting off that has 7 eV for that one, okay? Because, that would be 8 eV, okay? Because it's going from there to there. If it goes from here to here, that would be 7 eV. If it goes from here to here, that would be 4 eV. Now, the photon here the electron could fall to there, give off a photon with 1 eV, and then it could fall all the way down. So it'd be like 1 and then 7. It could go from here to here. That would be 4 and then 4 more. Hopefully that makes sense, okay? It could go from here to here. So anytime the electron falls down, that's going to emit a photon. Anytime the electron goes up, that would be absorbing a photon, which, think about the energy, that should make sense. When you look at hydrogen, for example, red was like the brightest line that you saw. That just means more electrons are falling down that have H times F of red color. So, and honestly, that's pretty much all of energy or photon emission, photon absorption. Make sure you go through and practice problems. Bye, kids. One more after this one.